Welcome to The Explainer. Today we're going totally under the hood. We're trading that familiar, friendly map interface you're used to for a somewhat gritty black and green digital terminal aesthetic. And there's a reason for that. We're literally going to peel back the layers of the invisible algorithms that direct so much of our daily lives. We are diving deep into the incredibly complex world of Google Maps AI.
All right, let's kick things off with a frankly mind-boggling number. 1 billion kilometers. That is the distance driven using Google Maps every single day, across something like 220 countries and territories. Just take a second to think about the sheer scale of that. To provide routing, live traffic updates, and exact ETAs for 1 billion kilometers a day, the artificial intelligence working behind the scenes to pull that off has to be absolutely extraordinary. So here is our flight plan for today. 1. The AI routing your commute. 2. Enter Ask Maps with Gemini. 3. The new rules of discovery. 4. Mapping the physical world. And finally, number 5, teaching AI to read maps. Let's get right into it. Section 1. The AI routing your commute. We're peeling back layer 1. Okay, so picture this. You're heading to a super important appointment across town, right? Mid-drive, your map just suddenly reroutes you. It sends you down some side street to avoid a massive jam that you can't even see yet. Now, how does it actually know to do that? Well, Google Maps partnered with DeepMind, Alphabet's AI research lab, to use things called graph neural networks. By crunching live traffic data along with historical traffic patterns, this AI is basically predicting a traffic jam before the slowdown even starts. And it works. It results in ETA predictions that are consistently accurate for over 97% of trips. Now, obviously, relying on historical data has a bit of an Achilles heel. When the COVID-19 pandemic hit in early 2020, global traffic plummeted by up to 50%. Driving patterns completely changed overnight. So the AI actually had to adapt. Those routing models were updated to become highly agile. They started automatically prioritizing traffic patterns from just the last 2 to 4 weeks, basically ignoring the older pre-pandemic data. It's just a brilliant, real-world example of machine learning adapting to human behavioral shifts on the fly.
Moving on to Section 2. Enter Ask Maps with Gemini, the conversational layer.
So we are currently watching the map transition from a standard navigation tool into a highly intelligent conversational AI assistant. The old way of searching was just basic keyword matching. You type coffee shop near me, and the map just pulls up places tagged with those specific words. Simple enough. But now, with Google's Gemini large language model baked into maps, we're shifting to intent understanding. This is a game changer. You can literally ask it, hey, find a quiet cafe nearby where I can work for a few hours, and the AI actually processes the context of that sentence. It cross-references reviews, photos, and business data to find exactly what you're looking for, not just matching the words. Which brings us to Section 3, the new rules of discovery, generative engine optimization. Because the way we search as consumers is fundamentally changing, local businesses really have to adapt to what's being called generative engine optimization, or GEO. You aren't just optimizing for traditional search rankings anymore. You've got to optimize for AI interpretation. To actually make these smart recommendations, Gemini looks at very specific data signals. We're talking comprehensive business profiles, specific contextual clues inside customer reviews, like someone specifically calling out great outdoor seating, high-quality photos so the AI can visually confirm those features, and super detailed website content. Basically, the AI needs all of these rich signals to confidently say, yes, this is the right spot for this user.
But that leads us to a pretty fascinating question. How exactly does an AI transition from reading digital text, like a Yelp review, to actually reading and understanding the complex, physical, 3D environment all around us?
Section 4. Mapping the physical world using satellites, SLAM, and sensors.
Okay, we are now dropping down into the heavy, under-the-hood machine learning layers. Before a map can be useful to anyone, the AI has to know where the buildings actually are. And relying on humans to manually draw building footprints on a map? Yeah, that is incredibly slow. Instead, researchers use deep neural networks to extract building footprints straight from satellite images. This framework takes flat, pixel-based images from space and automatically generates clean, recognizable geometric shapes. It literally teaches itself to look down from space, recognize a building, and draw a perfect box around it. No human intervention required. But what about inside the building? Satellites can't see through roofs. For that, we use something called SLAM, simultaneous localization and mapping. Basically, this is a camera-based system that records frames in real time to construct a virtual map. What makes SLAM so incredible is that it allows autonomous devices to map out an interior space dynamically. You don't need a human to renovate the space or, paint black guiding lines on the floor for a robot to follow. It maps the room and figures out its own location inside that room at the exact same time using just a camera. So how does the machine actually see that interior space? Well, it's a combination of inputs. First, you have plotted 2D visual keyframes gathered by the camera. Think of it like a digital breadcrumb trail of exactly where the device has been. Then, you combine that with a 90-degree LiDAR raycasting system, which is constantly firing lasers to measure exact distances to walls and objects. By fusing that visual map with the real-time distance measurements from the LiDAR, a deep learning model can successfully navigate a complex room and actively dodge unexpected obstacles in its path. Why does all this matter? Real-world impact, that's why. All this raw map data is converted into what's called an occupancy grid map, or OGM. Just imagine a grid laid over a room where every single square is tagged as either occupied by an obstacle or unoccupied and safe to roll over. Using an A-star search algorithm, which is just a fancy way of calculating the most efficient route, this exact technology is actively being used right now to help smart wheelchairs autonomously navigate complex interior rooms. It finds the safe, traversable paths entirely on its own. It's truly amazing stuff.
And finally, Section 5. Teaching AI to read maps. True spatial reasoning.
It's kind of funny, actually. If you look at cutting-edge Google research regarding multimodal large language models, MLMs, you find a pretty glaring flaw. Despite all the wild advancements we've just talked about, current MLMs lack true spatial reasoning. They are fantastic at identifying objects. If you show it a map of a zoo, it'll point out the lion enclosure instantly. But if you ask that same AI to draw a walking path from the entrance to the lions, it completely struggles. Because it doesn't have a grounding in the physical rules of our world, it might just draw a straight line right through a building or a brick wall or the gift shop. It literally doesn't inherently understand that you can't walk through walls.
So to fix this massive blind spot, researchers built the MapTrace pipeline. It's a system for generating synthetic training data to finally teach the AI some spatial reasoning. Step 1. It identifies traversable paths using an AI called a mask critic. This critic verifies which areas are actually walkable, sidewalks, versus, say, solid walls. Step 2, it converts that walkable area into a digital pixel graph made up of nodes and edges. And step 3, it uses classic pathfinding algorithms to draw a route, and then a second AI, the path critic, does a final quality check to make absolutely sure the route is logical and respects all physical boundaries. By running this automated pipeline, researchers successfully generated 2 million high-quality question and answer pairs. 2 million! And they've open-sourced this entire massive dataset to explicitly teach AI models the fundamental rules of navigation, connectivity, and how to visually follow a route without, breaking the laws of physics.
There's this quote from Google Research that just totally nails the ultimate goal of all this complex architecture. They wrote, "The ability to reason about paths and connectivity unlocks a host of future applications. Smarter robotics and autonomous agents, enhanced accessibility. We are talking about a future where visually impaired individuals can get perfectly accurate step-by-step audio routing through a chaotic, multi-level subway station, or rescue robots being able to navigate a collapsed building just by glancing at a floor plan." Which leaves us with this final thought for you to chew on. We've gone from simply predicting traffic jams to building an AI that can literally read, understand, and reason with the physical constraints of our world. When this level of technology is fully integrated into the devices in our pockets and the vehicles we ride in every single day, how will that fundamentally change the way you navigate your own life? Thank you so much for joining me on this explainer, and keep exploring.